Hello, good morning and good afternoon to everyone watching this. Welcome to another lecture of our summer crash course on feminist and ecological economics. And I hope this will be a good and useful lecture for you wherever you are and whenever you're watching. It's a bit strange to record beforehand with no one watching, but let's give it a try. Let me start by introducing myself. My name is André Cieplinski. I am a postdoctoral researcher in economics at the University of Pisa. And in the last 3 years of my academic career in work here in Pisa, I've been building and working with ecological macroeconomic models, more specifically simulation models. And we'll get, I think, a bit more into the specifics of different types of model during our live lecture and discussion. But I guess the point is that I have not always been an ecological economist, and I have not, during my PhD or even before, building models specifically and simulation models even more specifically is not what I've always done. So I found myself in this situation for work reasons, which I enjoy very much now. And what I'll try to do in this lecture is try to show you some things that I guess would have been helpful to me when I was starting to work with these models. And I'll try to focus on things that I think are more objective and then can be presented in a very general way, whereas some things that are more subjective and should be tailored according to your needs, according to a specific research question you might have, or a more narrow research area you would like to place yourself in. I think we should leave to the live lecture and discuss one by one. So what I will do is basically I will present two main building blocks, which are input-output for production, and then stock flow consistent models, or at least the basic of stock flow consistent models, which are some stuff that you will usually find in ecological macro models. And then we will together read through or develop a version of a model that is from Professor De Fermo's article, which is indicated as the main reading for this lecture. And I've always learned stuff going through actual models and actual manuals that other people wrote. So I guess this is a good way to show you what are the main components. This is a very much a simple but still very complete model for ecological macro. It involves a lot of areas, but with not so large level of complexity in each of them. So my idea here is that using this model, we'll be able to understand how different areas of the economy are connected to the environment, between themselves, and so on. So let me just share the slides so we can get started. And here we are. Let's get to the first slide. I'll put it on full screen. Okay, so as I said, I am André Cieplinski, and this is the title of our lecture, Ecological Macroeconomics, Modeling and Simulations. For now, we will be a bit more on the modeling and much less on the simulations, because simulations is one type of model, or is one methodology which you can use to run models. There are many others, such as agent-based models, which are also simulations, but I usually do system dynamics, which is a different kind of simulation. We'll get into that. But you can do macroeconomics models with econometrics, relying just on data and statistics, or you could also just develop an analytical model by yourself. The important thing is that whichever type of model you want to develop or use or read should have some internal consistency, and being in the ecological economics and post-Keynesian economic traditions, they will usually have some characteristics in common, such as the one that we will see today. Okay, so this is very much a disclaimer, this first slide. And as I said, here we'll try to provide an introduction to the main features that ecological macro models usually have. And hopefully the things you see here are things that you either saw reading other papers or the one I indicated, and that you will probably find similar, presented in a similar fashion in the future. So as I said, we'll focus on two building blocks, and then we'll develop the modified version of the model presented in the 2017 article indicated below. Then we'll discuss some tips and stuff that I think about and I think everyone should think about before starting to build a model. Okay, so here we have the main reference for this lecture. And then I just point some other articles. They are not mandatory or necessary in any way, but I think some of them are nice. One is by me. We'll see a part of it in the end when we discuss the tips. There is quite some stuff on material flows, which is cool and connects well, although we'll see a very simplified version of it today. And then we have this article, which is a review of many more or less new ecological macroeconomics models, and it lays down their characteristics, what they have in common and what is different, and could be a useful reading as well. So let's go. Here is an outline. So let's get started with our building blocks. So first and foremost, let's talk a little bit about input-output. So input-output matrices record all transactions of intermediate and final goods and services domestically and abroad between industries and from industries to households and individuals in an economy, and with other industries in other countries in the form of imports or in the form of exports. It is the primary methodology that national governments use to calculate GDP, to calculate national output. And I'll try to convince you why I think it is useful to always start from something that looks like an input-output, at least, rather than just relying on simple production functions. Never mind what kind of production functions, as like it could be a Cobb-Douglas, but it could also be just a simple Leontief production function. It is kind of different from using an input-output. And one of the reasons I would argue, specifically for ecological economics, is that accounting for intermediate trade, so the inputs that an industry have to buy to produce their final goods. So for instance, let's say manufacturing industries sell machines, but to build these machines, they buy several parts from, they buy metals from mining, they might acquire services from specialized firms that do, I don't know, design or R&D, and they acquire buildings for constructions where the factories are and so on. And so the idea here is that accounting for all this intermediate trade, not only for the final output, gives us a more accurate description of the total amount of goods, which is directly related to the total amount of materials and energy that are required and used in production. Okay, so if we have this better representation of the whole picture of what the economy demands to produce its final output and GDP, and we'll see the difference between these two very soon. It also gives us a more accurate picture of the environmental impact in terms of materials, energy demand, and therefore also emissions that is related to this production. Okay. Moreover, since the input-output structure or matrix accounts for inter-industry trade and how much one industry demands for the other or sells to the others, it also provides a pretty accurate picture of the effects of structural change or demand shifts in overall resource use. What do I mean by that? I mean that, for instance, imagine that consumers from one year to the other change their tastes and start acquiring, I don't know, much more, let's say, goods that seem to be environmental friendly and have less environmental impact. But then if you do that with an input-output model, you should be able to see the effect of this upstream, right? So you buy less of, I don't know, mining, and mining is not very much a good example because households don't directly consume from mining. So let's say you buy less goods from energy-intensive manufacturing and start buying less energy-intensive goods. The reduction of this final demand for energy-intensive machines, for instance, or it could be cars, will reflect upstream in how the energy-intensive industry demands less, let's say, less electricity it might demand less of other polluting energy goods to produce these machines, and more of, I don't know, less impactful or natural resources and so on. Let me, sorry, let's get through it. And finally, one point is that if you model through input-output, as we'll see what we mean by that in a minute, modeling technological progress endogenously can be tricky, and I'll try to get into that soon. Okay, so here we have the same slide with a simple representation of an input-output system. So here we have two industries, 1 and 2. Okay, so the Z's represent the intermediate rate. Okay, and this total means their total intermediate output. F represents the final demand, so consumption from households or investment demand by firms or exports. And the total output of Industry 1 in this economy is given by the final goods it delivers for consumption and investment in final demand, together with the intermediate goods it produces to sell to itself and to Industry 2. Okay, and the same thing goes for Industry 2. It provides inputs to Industry 1. It supplies inputs to itself. It could be, for instance, two different firms which are in the same industry, right? So one agricultural firm that sells seeds to another that produces the actual, I don't know, corn or other food products. So it sells these two types of intermediate, well, we sell the same intermediate good here for these two industries. And here we have the total, the sum of the two of intermediate goods provided by Industry 2, plus the goods it provides for final demand, again from consumption, investment, or exports. And here we have its total output, right? In the bottom, what we have is, so as we saw here, Industry 1 on the columns is the one that demands. So it demands intermediate inputs from itself or other firms in the same industry, from Industry 2. Okay, so this sum is how many total intermediate inputs are demanded by Industry 1 to produce this total output. But it also demands imports from industries like itself and like Industry 2 from abroad. Okay, so that the total amount of goods required for production of this output by one is intermediate from itself, intermediate from the other industry, plus imports. Okay, and finally, we have value added. Okay, so value added is just the difference between total output and intermediate inputs. Okay, so it is the value of final output that is not paid for the acquisition of other goods. And as we'll see, usually value added, there are more items, but it can, for simplicity, be split between profits and wages. So all the value added is determines, or doesn't determine, but is split, and we get the distribution of that income between wages and profits. Okay, so this is just a simple representation. As I said, here on the column going up to Industry 1, we have the inputs that Industry 1 will use to produce its output. And the same thing here, right? From the imports to the other intermediate goods. And on this direction, on the horizontal, we have the outputs. So how much Industry 1 is supplying to Industry 1, how much it is supplying to Industry 2, how much it is supplying for final demand as an output. So this is just to remember, because now we'll see an actual example with actual data. So just some identities which are common to find in models and elsewhere, which should be helpful to remember. So as I said, total output Y, okay, as the sum of the output from the two industries, is defined as Z, total. So the amount of sorry, the amount of intermediate goods produced plus the amount of final demand. Okay, but at the same time, this is equal to the amount of intermediate goods plus imports plus value added. Okay, but why? So we can define GDP in three ways, which is common, like to be presented in economics textbooks, from the expenditure side, from the income side, and from production side, right? From the expenditure side or demand, what we have is that GDP is equal to the final demand, okay, minus imports. So it's the total demand, final demand, there is directed to domestic industries. This is the value of the national production. This, on its turn, is equal to the total value added, which is nothing but the value of total output minus intermediate and imports. Okay, so we take Y, which is the value of the total output, minus the value of intermediate goods used for this production, minus intermediate goods from abroad, and this difference is the value added, which is the actual value created in this economy during the year or the period in which the input-output is being recorded. Okay, so here, once again, we can, from this equation, we can work it out, no, from these two, and we can see that Y, apart from being equal to the total intermediate production plus final demand, is also equal to value added plus imports plus intermediate demand, right? But when we do an input-output in a theoretical or a simulation model, we don't have the actual values of intermediate trade, right, or of imports. Usually what we have is some value of final demand, which we get from consumption. We have like a behavior equation that will give you the consumption of households, another behavior equation that will tell you how much firms want to invest for a given capacity utilization or interest rate. And from there, we want to find out what the output will be. How do we do that? I'll show you in a minute, but basically we build a matrix of technical coefficients A. So it's kind of simple. We simply divide in the initial period, from the data we have, the intermediate demand from industry 1 to 1 by its total output. Okay, so the sum of these three would be Y1. And on the same way, we can do it for all the elements of the input-output matrix. Then, if we subtract an identity matrix from this technical coefficient matrix, we get ID minus A, whose inverse is actually the Leontief matrix. Okay, so if we have a fixed technical coefficient matrix, so think about it. What does each element of this matrix tells us? It tells us that for the production of 1 unit of output in industry 1, you need Z11 unit of intermediate input from 1, and you need Z21 units of intermediate output from industry 2, and the same way for industry 2. So basically, it tells you for each unit of output of the industries you have, how many intermediate inputs you will require for production. Okay, but this might be a little abstract, so I will stop sharing these slides for a minute, and I'll show you simple spreadsheet. Sorry. So what we have here is an actual input-output matrix. This is the Italian input-output matrix by industry, 63 industries from 2015. So this is just to show you how it will actually look when you download something. And sorry, this is a bit confusing, but what we have here are the supply in industries, and here the demand in industries, and here inside the matrix we have the values of the intermediate trade between them. Okay, but this is a bit too much, so what I did is I aggregated all that matrix to less industries. So for instance, in the beginning here we sum production of vegetables, animal and hunting products with fisheries and so on, to build one simple one larger aggregate industry for agriculture, mining, manufacturing, utilities, including electricity and water, construction, trade, transport, services, and public sector, which includes education and health in this case. Okay, so in the exact same way, now we can see with numbers what we were talking about. So these 7, for instance, these values are in million euros, I guess, or maybe, no, it's millions. So mining requires 7 million inputs, 7 million in inputs from agriculture to produce its output, okay? Which is 35 billion for intermediate outputs, plus 10 in final demand, plus, well, the sum of these two makes its final output, right? 45,000. So just to give a clear example, if we sum all the supply from agriculture, so this row, we get its total intermediate supply, 45,000. And then here we have its final demand, which is split between consumption, government expenditure or consumption, investments, and exports, which sum to 27,000. And if we sum both of these, so intermediate inputs and final demand, we get the total output of agriculture, okay? And the same way for mining, for manufacturing, which, as you can see, is much larger than agriculture, and so on for all the other industries, right? In the same way, you have, once again, agriculture as the demanding sector, and it demands 6,000 million from itself, 45 from mining, 10 billion, well, 10,000, which is actually 10 billion from agriculture, from manufacturing, apologies, and so on from all the other industries. So here, this number, 24,000, corresponds to the total demand of intermediate goods that agriculture needs to produce its final output, okay, plus imports, which are down here. So this is the total demand of agriculture, of intermediate goods, domestic and from abroad. Okay, the reason why I wanted to show you this is that I just wanted to show you the calculation. I will share this with the organizers and they'll make sure you get a copy of it. Here I wanted to show you that you can calculate the GDP in 2 ways, very simply. So we have the sum between value added. Okay, so to get the precise value, you have to adjust value added by taxless subsidies. If we sum these two, we get this value for GDP of 1,524 billion, which is the nominal Italian GDP for 2015. But we can also calculate it from the expenditure side, which is just the sum of final demand, so the sum of total consumption, government, investment, and exports, minus imports. Okay, so we, sorry, it's the one in the bottom. And here it is. We have to subtract this value from the total imports, and we get the GDP once again. Okay, I have everything prepared to calculate the Leontief and obtain the the output from our technical coefficient matrix and the inverse of it, or the Leontief inverse. But I'll send it ready to you through the organizer, so you can play with it. Okay. Just to emphasize something we said earlier, what we have here is, for instance, the GDP, which is 1,500, but total output, which is, okay, sorry, not 1,000, it's 1.5 trillion. But at the same time, we have the total output, which is of 3.5 trillion euros. Okay, so as I said earlier, if we don't take care and pay attention to all the intermediate inputs that are here, we risk losing a big size of the total demand for materials, for energy goods, for renewable energy as well, that the economy will have for a certain production. Okay, so let's go back to our slides now. Okay, here we were. So this was input output, and I think we took perhaps a bit too long. but I think we'll probably accelerate from now on. So now let's talk about stock flow consistency. Stock flow consistent models emerged among post-Keynesian economists, in post-Keynesian economics, working on analytical, sometimes econometric and agent-based models in the past. And it is, sometimes people will refer to it as like a methodology. I think it's more like an accounting framework, which guarantees that you are actually considering all the stocks and flows in an economy and the transactions between all agents. And it is embedded in the actual larger paradigm of post-Keynesian economics, right? So why is it relevant for us? What does it do? It provides an accounting framework, as I said, that specifies the balance sheet and transactions between the different types of agents in an economy. So in a way, if you set the stock flow consistent matrices, before you actually do your model or after, just to make sure things are all right, if it works well, you will guarantee that all expenditure by someone becomes revenue for someone else. So agents or households consume, and that consumption is revenue for firms. Okay, firms invest, but that expenditure investment is revenue for other firms that actually perform the investment, right? In the form of building factories, building apartments and houses, or selling machines, for instance. Or, for instance, taxes are an expenditure to consumers, but they are revenue for the government, and so on and so forth. And in the same way, it also guarantees that all liabilities have corresponding assets. Okay. However, as I said, this is very much an accounting framework in the way we will show now, and specify the transaction and balance sheet matrices do not specify behavior equations or the causality between equations. Okay, which is basically your role as a modeler, and well, not just as a modeler, as an economist, as someone who wants to build a model. Whoever you are, everyone can do it. And it also, well, in the meanwhile, it helps us keep track of all the stocks of real and financial initially, but as applied to ecological economics, it also helps us keep track of the extraction and use of natural resources. And we'll have an example of that with our model. So usually what we have is that in models that consider stock flow consistent models, an increase in these stocks, which is wrong, sorry, an increase in the stocks will have a feedback in the economy. So let's think about wealth, for instance, right? We have, you have an income and you consume, say, 70% of your total monthly income, and 30% is automatically becomes savings, right? You save and you put it away, and that adds to your wealth stock. Okay, so the idea here is that variations in the total stock of the wealth, for instance, of the agents, will have a feedback in the economy. So if, for instance, you have, say, 50% of your wealth in equities, okay, it's a bit too much, but anyway, you have some part of your wealth in equities from firms, and the price of these equities increase, I don't know, say something like 30% from one day to the other. So you will have like a large increase of your wealth, and this perceived increase in your wealth will somehow probably convert to most people into an increase in consumption. Okay, and it could be the other way around. You have a negative wealth shock that, okay, let's make a bad example. Part of your wealth is housing, if you are lucky enough in 2020 to have a house of your own. There is a natural disaster that destroys, let's say, half of your house or all of it, and destroys all your wealth. So naturally, this negative wealth shock will lead you to probably consume less in the near future and try to save more to reestablish and buy another house and so on. Okay, so the idea is that also keeping track of the stocks will eventually allow us to understand and better specify how variations in this economic, but in our later example, also natural resources stocks have a feedback effect on the economy. Okay, So I will show you two example matrices of a stock flow consistent model now, which are largely based on this article, okay, by Claudio dos Santos and Gennaro Zezza from 2008. You can look at it if you want. Let's go. Okay, so we said there are basically the two most important things are two matrices, the transaction and the balance sheet matrix. So the transaction matrix usually will specify all the transactions. So expenditures and revenues between different types of agents in an economy, whereas the balance sheet matrix will specify the stocks of assets and liabilities belonging to the same institutional sectors. Okay, so for instance, here you have in the columns the sectors, right? Households, firms, which have a current and a capital account. We'll see the difference between this one. Then we have banks and government in this example. And on the rows, we have the different transactions, right? So what is this telling us? This is telling us that households spend money in consumption, minus C, and the total amount spent by households in consumption becomes revenue for firms, okay? In the same way, government spends G, okay? And that becomes a revenue for firms as well. I think here I inverted actually. It should be then firms, firms pay investment I, and that becomes capital, is incorporated. This investment is incorporated into firms' capital goods with plus I. Sorry, I inverted the sides here. Just to continue, so firms have these revenues from the government, from consumers. Some firms have positive revenue for investment, others that do not perform investment but just acquire to expand their capacity have negative. But then they have these revenues, but they pay wages to the workers they hire. So wages is an expenditure for firms and the revenue for households. Here we have taxes, and as we can see, there are some taxes paid by households and some by firm, and they all end up as a revenue for the government. And here we have the transaction related to financial assets. Okay, so firms take loans from banks to perform investment. And so every period they would pay L, which are loans multiplied by an interest rate R. And that payment for loans is revenue for the banks. Okay, but we can also look in the column and see, for instance, let's check just the bank. So the banks, they receive payment in the form of interest for on loans from firms. They receive interest rate from bonds they own, paid by the government, okay? And then what do? They pay a smaller, usually interest rate on deposits, which constitute the wealth of the households. And the difference between these two will be banking profits, profits B for banks, and it will be distributed, in this case, to households which own the banks, okay? The same thing for firms. If you sum the column here, what you get is all the revenues minus all the expenditures from the firms, and the result of it is profits. And the profits are paid to households. Okay, so what you can see is that all the rows sum to zero because everyone's expenditure is someone else's revenue. And here you see that summing up in the columns, what we get is the famous expression that investment equals saving, right? The total investment will be equal to the savings by household and government, which, by the way, could be a deficit by the government. It's not a problem. But note that this identity does not specify the causality. So we're not saying that households must save more so that firms can invest more, but neither is this metric saying that if firms invest more, households will save more. Okay, this will be defined by the behavioral equations of the model that you or I or everyone who wants to build a model will develop. And here is the second matrix, which is the balance sheet matrix. And what we have here is the stock of assets, right? So here we have transactions, and the idea is that these transactions will feed in stocks. So household saving in the end of a period will become deposits, because households only have deposits. Okay, just to give you an example, or equities, right? Sorry, they have deposits and equities, and the reason why they receive profits from firms is because they own the equities of the firms, right? So what do we have here? We have the same institutional sectors on the columns: households, firms, banks, and government. And on the rows now we have the assets. So deposits, loans, and bonds, which we had seen before, equities, and capital goods. Okay, capital will be the assets of the firms. So if we look in the columns of each institutional sector, what we have is basically the balance sheet of every one of these groups of agents. Okay, so for instance, let's look at firms. Firms have loans which they own to someone, the banks, and they have equities which they own to someone, households, right? Households earn equities, and that's why they receive profits. But what is the counterpart of these liabilities? An asset, and the assets are capital goods. Okay, the fixed capital that was built by the firms through investment and so on. And the same thing goes for banks, for instance, right? So the banks, they have as assets loans, so they gave loans to firms and they receive money from interest payments, and they bought bonds from the government and they receive interest from government bonds, but at the same time they own deposits. So the households put their savings as deposits in the bank, and the bank owns that money that are in the form of deposits to the households. Okay, so we can use that to build, it's very in the bottom here, I'm sorry, but build very simple balance sheets for these institutional sectors. So here we see for the firms, we have capital goods as assets, and both loans and equities as the liabilities, and the sum of these two must be equal to this. And the same thing for banks, right? And here what we see is that if we sum everything, we get just capital, right? Everything else cancels out. And if we sum everything here, we have bonds and the total net worth of households, which is the total value that they own in the form of equities and deposits. And finally, what we'll have is that capital, so total assets of the economy, will sum and be equal to these two. Okay, I think we have been in kind of a long time here. And now we can move on to the perhaps the main part of this lecture, which is developing a model based on the article we talked about before. And this is kind of long, and I will not perhaps go through each and every equation, but when you get the presentation, I put the comments so you can work through it yourselves, and perhaps it will also help you read the paper in case you found it difficult, because it's not difficult because the equations themselves are not difficult, but there are many, and there are specifically many interconnections between them, which sometimes is hard to keep track of. So what we'll do now is that we'll take a look in these different parts of a model, which I would say is that ideally is everything you would like to have in an ecological macro model. Not necessarily you will always have this. For instance, I never did a model that had all of this. But we'll discuss why and what you should have afterwards. And then once we are done with the equations, we will try to use this model. Well, we will try now. We will build similar matrices to this, but starting from the model that we are looking at. Okay. So a tentative model, as I said, let's move this. Sorry, it's in front of the slide for me. Okay, no, yeah, better no, sorry. So, as I said, we'll develop a version of the model presented by the firms et al. In 2017. And this model comprises a simple global economy, okay, so the whole world, which has consumers, banks, and firms, but no government. And we will model the economy in different parts of it: energy demand, greenhouse gas, simplified as just CO2 emissions, some materials extraction and consumption, and waste. Okay, this slightly generalized version of the paper that I present to you have two industries because I added part of the input-output. Has homogeneous households which consume goods. We have two energy sources, renewable energy sources here and non-renewable, and we have only commercial banks. Okay. So from now on, we will comment on the equations that build the model, but specifically, we want to focus on the difference between behavioral equations. So where you as a modeler will specify causality, will try to understand which phenomena leads to an increase in investment of consumption or a change in technology, and which of the equations are actually constraints, okay, which you must respect to make your model consistent. And second, we will also try to talk a little bit more about the interaction between economy and environment. Okay, so first part, we'll start from production. And here, once again, production is a simplified version of an input-output. So we have in the first equation here, final demand F, which is given simply by the sum of consumption and investment. Okay, so I, the index stands for the two industries we have. So, okay, we'll see later, but households consume goods from industry 1 and 2. And both of them perform investment, and this will result in final demand. Okay, we will obtain the total output multiplying the final demand by the Leontief inverse. Okay, which okay, I hope you will work through the Excel spreadsheet I'll send to you, but you can also find online resources to explain. But it's okay. Let's go on, otherwise it will be late. But hopefully it will be helpful. Otherwise, we can develop it more during the lecture. Okay, and here we have a maximum output, which I'll explain in a minute. But for now, we'll focus on output as a function of the Leontief inverse multiplied by final demand. And in the same way, if we multiply the technical coefficient matrix, so remember the one that specifies the intermediate input requirement for each unit of output, multiplied by output, we'll get the Z matrix, which represents the intermediate inputs supplied and demanded by each of the two industries. Here, once again, we have an accounting identity, right? So what is this? This is the GDP. So the sum of final demand in both industries. Remember, it's a global economy, so we don't have imports now. The sum of the two final demands will be equal to the sum of the value added in the two industries. And finally, this value added is distributed between wages W and profits P. Okay, so now we can move to the maximum output. So what we are doing here is we are assuming that this is a demand-led economy and final demand will determine output. However, there is a maximum output that these industries are able to supply, and this maximum output, Y bar, is a function of YK, YL, and YE1, E2, which stand for energy source 1 and 2. And okay, yeah, as it's written here, the production capacity is limited by the availability of capital goods, of labor, and of the two energy sources to satisfy the final demand. All right, so for instance, YK will be given by the amount or stock of capital goods an industry has, multiplied by a fixed parameter V, which represents capital productivity, right? So capital productivity here is simply a fixed ratio that tells you with 1 unit of capital good, I am able to produce 3 units of output. And the same thing goes for labor. So with 1 unit of 1 individual, which is in this case is specified as individuals, working age hours. Okay, so here we would specify the, let's say, yearly hours the average worker works, 1,500, 1,600, depending on the country, multiplied by labor productivity, right? So productivity, how much an hour of work results in output. Okay, so check the function and we see that the minimum between these two, so the one that is lower between YK and YL will constitute the actual constraint. So if I am not able to hire more, okay, this is rarer. Let's say if I don't have enough capital goods to satisfy demand, then to satisfy my final demand, then I'll produce less than I would given by this, right? And I'll be constrained by the maximum. And then we specify also for the energy, let's say there is an energy supply, and I would say here it would only be binding for the non-renewable resources, right? Not for electricity produced out of wind and solar, although it could be in the short term, but if we're dealing with a long-term model, not so much, because we can always increase productive capacity with its constraints of material demand and land use and so on. Okay, so this AYY, so I will not go into this because it's mostly what we said already about building the the technical coefficient matrix. So this will be one element as we've seen in the Excel file. But this will appear again later. This is the UI, stands for the capacity utilization. And what it's telling us is, so it's just a proportion between the actual output of an industry and how much its capital is capable to produce it. So it will serve as an indicator of when I need to invest, right? So if I am producing at almost 100% of my capital, of what my installations, factories allow me to produce, probably I want to invest more and increase this capacity. If I'm producing at 50%, there is probably no reason why I would like, as an industry or as a firm, to make an investment. Okay, so after production, we can go on to the two factors that compose our final demand. First, consumption, and then investment. For consumption, we'll have the households as consumers, and they will consume out of their disposable income, YD. And basically what these equations telling us is that households earn income from labor, okay, in the form of wages, from interest on the deposits they own that are in the bank, so from their wealth accumulated. And they also, as owners of equity, they receive dividends in the forms of part of the profits from the firms and the banking profits, BP. We'll then say that consumers, actually a fixed proportion of their income will be converted in consumption. Okay, the classical marginal propensity to consume that I guess everyone that studied economics has seen in some form in a textbook. So little c multiplies YD, but also, as I mentioned before, one of the advantages of having the stocks of wealth is that we'll also have a marginal propensity to consume out of wealth. So if I saved a lot in the previous period and my stock of wealth increased, I'll probably increase consumption a little more this year. Usually this marginal propensity, as it is out of a stock, is much smaller than this one, right? And finally, here, one of the first feedbacks, we will specify CD as climate damage. Just to give it a feedback, we'll get to how climate damage is modeled in a very simplified way, but here the idea is that an increase in climate damage from higher temperatures or natural disasters or other consequences, sea level rise, we'll go more to the future, could affect the availability of some goods or sharply increase their price, thus reducing consumption. Okay, so these two equations will just distribute this total C consumption between the two industries as a fixed alpha proportion. And here we have again an accounting identity. The difference between all the income they earn minus consumption is savings, and savings add to deposits. Okay. Then we can move to banks, which in this example model is very simple. Banks simply hold deposits from households, and they make loans to firms, H, loans are H, D for deposits. And we can define the bank profits, BP, as simply the interest that they earn from the loans. Okay, so the summatory of interest on the loans of the two industries. Here we specify the past period, is the revenue, and their cost, which is the interest that they pay on the deposits from the households. Okay, So very simply, the amount of loans increase according to this equation, but during the investment part, we'll specify the variation of loans, which depends on firms' leverage. And then this is just an identity to equate the balance sheet of the banks. And we will assume that the interest that they receive on the loans, or actually the interest rates that they ask on loans, is higher than the interest rate that they pay to deposits, which is close to, we would assume, the basic interest rate in the economy. So they add a fixed markup here, which is greater than 1, such that they have positive profits. Okay. Here, this is a bit more of a complex part on investment in industries. However, as we saw before, the value added of an industry is the difference between their poorly written output and all the intermediate inputs they use in production, including imports. But here, remember, global economy, so we don't have imports. So here, that's what we have in the first equation for industry I. The value added is given by its total output minus the the intermediate inputs from the two industries J, which are itself and the other. Okay, so it would be the column of the input-output matrix we saw. And then we can specify profits from the firm as simply the difference between value added and all its other costs apart from intermediate goods Z. So value added minus total labor expenditure, hourly wages, again multiplied by hours, multiplied by number of employees, minus how much they pay to banks as interest. So interest multiplied by the stock, the outstanding stock of debt. So here we will simply distribute profits in two parts. The first part is dividends, DP, paid to households. And the second part is retained profits, RP, 1 minus DPI, which will be used to pay for investments. We'll see in the next slide. Once again, we specify like this motion equation for capital goods. So the stock of capital goods in period T will be equal to the stock in the previous period, 1 multiplied by 1 minus depreciation. So how much capital goods you lose due to wear and tear in the period, plus the investment, which constitutes new capital goods. Okay. Finally, we can specify labor demand of each of the industries as a function of its output, Y, okay, and divided by the total number of hours worked, which is fixed, and the labor productivity. Okay, remember this equation here. So it's basically we are just inverting. So if we pass lambda, which is the labor productivity, and H here, we get Li equals to output divided by these two. And finally, we will not add a lot of motion in hourly wages. We'll just assume that hourly wages are a fixed omega proportion of labor productivity. What does that mean? It means that for every hour of work, I produce lambda, which let's say I produce for every hour of work, I produce 10 goods or 10 money's worth of goods. And a proportion omega of that is paid as wages. So say that this is, for instance, like 70%. So 70% of the value produced in an hour is converted into wages, and the remaining 30% will become profits. Okay. So next, and this is perhaps the more complicated part of it. So first thing, in this first equation, we'll specify desired investments. So here we have a proper behavior equation that's telling you, so here we're making a judgment, right? This is not an identity. We're saying that investment or how much firms want to invest is a function of capacity utilization U and depreciation. So firms invest to recover the depreciation that they had in the previous period, but they also invest as a function of capacity utilization. So once again, if I'm using almost all my capacity, my industries, my factories, I will want to invest more So we have an alpha, which is positive. And then we can add an intercept, which is common. Sometimes people call it animal spirits or something else, but okay, this is just a simple specification. But what we see here, once again, is the function of climate damage reducing desired investment. However, we will, okay, so why are we calling this desired and not actual investment? Because actual investment is not given by how much, it's not, I'm a firm, I want to invest $1 billion, I will invest $1 billion, right? So what this means is that actual investments, define equation here, I, depend on how much of the desired investments firms can actually finance, okay? And they'll finance this, part of it using the retained profits, RP, that we saw before, and the other part of it with new loans, okay? So delta H, so remember H stands for loans. The important part here, this is just a generic expression, but ID minus retained profits, what is this? This is ideally how much I would like to finance in terms of loans, right? So if I want to invest 100 and I have 20 of retained profits, I would like $80 or some other money in new loans to finance this investment. But we'll multiply this by a function of leverage. Okay, so leverage total loans divided by total capital. So what this is nothing but a measure of how indebted a firm is. Okay, so the idea here with the function having a negative first derivative is that the higher the leverage, the more indebted you are with respect to your assets, the harder it is for a firm or an industry to finance itself. So if you already have a lot of debt and you have not repaid it, you will probably, as you see, it is decreasing in leverage. You will probably not be able to finance all your desired investments. Okay, so we just bound the function between 0 and 1, meaning that at the low, after a certain point, the lower your leverage is, doesn't matter, you will always be able to finance 100% of what you would like. Okay, and so the actual investment is the RP, which you can always do if you have retained profits, plus how much more you can finance in terms of new loans. And as we saw, here we have a feedback again, right? We have a feedback from loans or debt to investment in the economy. So if I'm a firm or an industry and I invest a lot in a period, maybe I'll grow or whatever, something else. But at the same time, I will accumulate loans and debt that will require payment in form of interest in the next periods, which will reduce the amount of investment I can do in the following period. And it works the other way around as well. Okay, so now let's finally get into the energy emissions and environmental part. This has been very economics focused so far. And we are almost in an hour, so we should hurry up. So what we did here is quite simple, but it's actually not a bad way to model this in real life. We are assuming that the energy demanded by industry can be, so ED is a function of its production by output again, right? And it's split between renewable energy sources, RES, and non-renewable, which we call NR. So let's focus for a little bit in this small matrix here, epsilon. So epsilon is indexed on the two industries, I, 1 and 2, and on the two energy sources, E, renewable and non-renewable, right? So assume that I get data in the beginning when I want to start my model. So in the first period, I will check how much industry 1 produced in terms of output and how much renewable and non-renewable energy it demanded, okay, for this corresponding amount of production. And then I'll calculate these ratios or energy intensities. And I'll say that the energy demand for energy Y, for industry Y, is the sum of the two renewable and non-renewable energy sources, okay, of this ratio. So Y divided by epsilon. So I here know that for every you can invert this, right? So E epsilon 1 res is equal to this expression. So the energy demand for 1 res is equal to Y divided by epsilon. Okay, so it's just an energy intensive. I know that industry 1, for instance, can be more intensive in renewable and 2 more intensive in non-renewable from the data. And this is what this matrix will express. So here, okay, going back, we express the energy demand of the two industries as the sum of their energy demand for the two sources. Or we can express the total demand for renewable energies as the sum of this column, right? The sum of how much industry 1 demands of renewable energy and industry 2. And the same way for non-renewable energy. And the total energy demand then may be defined in these two ways, as the total energy demand of the two industries or the total energy demand of the two energy sources. They will sum to the same. Okay, and just to finish with energy, the stock of non-natural resources we'll assume is a decreasing function of the demand for non-renewable energy, right? So it only decreases in this simple case. In real life, it could increase because you could find new oil wells, you could find new coal mines, and so on, and this will increase the actually known stock, which is how the original model does it, by the way. But here, for simplicity, we're just saying that the more non-renewable energy you use will reduce the stock of non-renewable energy, right? And that, as we saw, I'm sorry to go back, could have a feedback effect on production as, for instance, if the stock of non-renewable energy gets too low, it might actually limit how much total output you're able to produce if you don't change technology to a more renewable energy intensive technology. Okay, emissions and climate change. So a disclaimer here is that this is very, very simple. And I honestly really don't know how to do it in a much more complex way. But this is here, one, to close the model, because we need to specify how production and demand and energy use result in emissions and temperature change, and how that is converted into damage to close the climate damage that we have feedbacking into our economy, but also to specify the different types of emissions and how emissions actually become increasing temperature in a very, very simplified way. So the first thing we'll do is that we'll consider two types of emissions. So from production, CO2y, y as the output, and a second type of emissions from land use. Okay, so deforestation, for instance, is land use. In a very simple way, we are just assigning emissions intensity, theta, to the use of non-renewable energy. So we saw that demand for energy can be in the form of renewable or non, and demand from renewable energy is not converted into CO2 emissions here, only E and R, which is demand for non-renewable, multiplying this by a fixed parameter theta, which just tells you that on average, if I use, I don't know, 1,000 kilowatt hours of oil, that will result in a certain amount of gigatons or tons of emissions. Okay. Sorry. Then, as I said, land use is here. It's not modeled at all. We just assume there is a decreasing trend given by this parameter LR. And this is very simplifying. It's just saying that like deforestation is reducing, for instance. But it's just important for us to remember that not all emissions are from industry. Some of them are from land use, which is also anthropogenic, by the way, most of it. So here we have total emissions as a sum of these two. And here CO2 at AT stands for atmospheric concentration. And what we see again is a function of the previous period. So the concentration in period T is equal to the concentration in the previous period plus this expression. So why are we not summing all the emissions? Because as we know, not all emissions become actually, well, remain in the atmosphere. Part of it goes back and is reabsorbed by carbon sinks from, for instance, growing vegetation, afforestation, or a good deal of it is actually absorbed by oceans, right? So only a fraction smaller than one of total emissions actually end up in the atmosphere every year. And finally, we'll just assume that this increase in concentration converts into higher temperatures. There are many ways to do this. Really, it's a bit out of my knowledge zone. Just to go back, temperature increase, so actually not increase, but the mean temperature is an increasing function, G, of the concentration of CO2 in the atmosphere. We know it is a function of all greenhouse gases, not just CO2, but this is a simple simplification, or we could imagine that here we are representing total greenhouse gas emissions in CO2 equivalents, for instance, right? And finally, again, my very simple assumption, we assume that the function climate damage, which we saw impacts both investment and consumption in our model, is just parameter multiplied by temperature. And here we specified that parameter psi is different between industry 1 and 2. And that is just because it's common to do. For instance, imagine that industry 1 is agriculture and 2 is services. Then we probably would expect an increase in temperature to have a higher impact on agriculture. In some places, most of the global south around the equator, probably very negative, but also in some places way up north and south, although there's not a lot of landmass to the very south of the globe, it could actually have a positive impact, increasing arable land, or I don't know, maybe allowing countries that were previously very cold to grow new crops. So it's important to understand here. So the reason why we use this is to make it clear that climate damage, temperature variation can have different impacts on different industries in an economy, as it can have different impacts on different types of households living in different places. Okay. All right, so the final part of the model, finally, is materials, waste, and recycling. So it's here's a disclaimer because I'll be talking about myself as well. Very often models are very much economic models, and then they consider the emissions that are related to production, but they sometimes, or most of the times, do not consider the material impact. Okay, so how many, I don't know, metals or rocks, squaring, sand and water and wood or whatever other materials are required to produce the output that, you know, produce the goods and the services that we demand and use in our everyday lives. Sorry, it's been long and I'm kind of losing my voice now. But here we'll just, okay, so our environmental impact in this example model will also consider material extraction. So total material extraction, M, in this expression here, is a function of output. Once again, a lot of things are a function of output. But it's also a function of how much you have of stranded or disposed assets, okay, which is, as we see, related to capital depreciation here, and is also a function of recycled materials, which is part of this. So for instance, I produce output Y, and that is related to a demand in, I don't know, gigatons of materials, okay? All the materials we talked about, wood, rocks, and whatever. But every period, also part of my previous capital goods stock, which is depreciated, so delta K, is converted into stranded or disposed assets, DE, but part of it is recycled. Okay, so part of DE becomes RE, which is recycled. So the total material extraction we can develop from these three equations will be a difference between these. And finally, we can say that the economic stock, or the stock of economic assets, is given by the one in the previous period, plus the amount of new materials that you use related to your output. So buildings, roads, or whatever used material or furnitures, minus the amount that is disposed. Okay. And the stock of materials of the globe decreases with the extraction of new materials. Okay. Of course, this is a simplification because we have an infinite amount of different materials we use, demand, and they're finishing. Some are rarer than others. But this is just to specify that, to go a bit beyond emissions, right? In the same way, another material we use when we emit CO2 is oxygen, okay? And here we'll say that oxygen used will be the difference between the amount of CO2 emitted by the industries in production minus the mass of the initial energy, non-renewable energy sources. So think of it as coal, for instance, right? So if we divide the total CO2 emitted from coal by a specific coefficient that tells you that every ton of CO2 emissions from coal corresponds to 3 kilos of it. I have no idea if this is close or far from what it is in reality. So the difference between the amount of carbon initially and the amount of CO2 emitted is given by oxygen. Okay, and finally we'll have waste here in the bottom, WA. So waste is just the difference between all the inputs and outputs in material use. Okay, so you have all the materials demanded and the mass of non-renewable sources and oxygen minus CO2, and you can show that it can be simplified as the difference between the disposed assets and the recyclables. Okay, sorry, this took very long, but we are almost there. Okay, so sorry, why is this important? Here it is. This is a very nice graph, although very sad, from a 2020 article published in Nature, whose reference is here in the bottom. And this is an estimate, I believe, of the mass of anthropogenic masses, which would be close to the economic stock that we mentioned here, right? So the amount of materials that are extracted and used to build infrastructures for humans. And what this graph tells us is that probably around 2020, the amount of anthropogenic mass on Earth has surpassed the weight of the total biomass on Earth. Okay, this is the dotted lines are the confidence interval of more or less what we think the weight of our Earth's biomass is. Okay, so on average, probably there is more weight on economic infrastructure materials used for humans than on biomass, apparently, since 2020, which is a very astonishing figure, and a big part of it and the growth seems to be concrete, which also emits, by the way. So this figure is just to show that it is something important. Okay, so I will not go through this because we wasted a lot of time, but it would be cool if you could work it out yourselves using the equations we saw previously. What we did here is we build also physical stock flow matrices using the emissions, energy, and material equations that we developed. So if you go through this, especially in the column sense, you will identify these relations in these three parts of our model. So here you see, for instance, the stock of non-renewable sources minus the amount of non-renewable energy demanded and how much you have period after, right? So you use non-renewable energy, you reduce the stock. The same way for materials, we have a stock of initial materials, use more, and then we have less of all the Earth's materials. Sorry, this shouldn't have the I index. This is wrong. It would be nice if you could work this out before the class and then we can discuss it. And I did the same thing. So once again, building the transaction flow and the balance sheet metrics that we saw before in the example, but now using just the equations that we see from the example model, right? So here you have the households, all they earn, minus what they spend, and it turns into a variation in deposits, and deposit sums to the household stock of wealth. Okay, so go back, think about what we discussed in the stock flow consistent model part, and then you can come here after the model and see if it works out. It probably does, I hope so. But it's cool, it shows you how you can take a model and you can write it in this way to make sure that everyone's paying to someone, and all the stocks also have corresponding liabilities and so on. And then we could come here and say, okay, but so the variation in this stock of loans, does it have an effect in our model? Anything? Yes, it does, because it changes how much I can finance of new investments. What does the variation in the stock of capital does? It probably has an effect on capacity utilization and how much firms would like to invest. What about deposits? It changed the wealth stock of households and will also have an effect on their consumption. Okay, so now we can move to the final part of the lecture. I am very late, I'm sorry, but these are very easy tips that I think we can discuss more afterwards during the live lectures. So first, behavior equations and accounting identities. As I tried to argue, relying on input-output and stock flow methods to build a model will naturally impose many constraints and accounting identities that you should respect. Therefore, I think modelers should pay special attention to the behavioral equations required, sorry, it's wrong, in a model, which is where they actually should take their decisions, right? Specify causalities, specify different functional forms, and deal with parameter and structural uncertainties. We can talk about what these are later, but this is just examples from our model. So this is an identity. We know that GDP can be calculated in these three ways. This is also the variation of a stock. We know this thing, the materials, add, the disposed, reduce, and change the economic stock. And this is also an accounting identity. The difference between the income that I earn and my consumption is savings. Okay, and there is not much you can or should do here, but here there's a lot you should do. So is my desired investment a function of capacity utilization and depreciation, or should it also be a function of my profit rate? So here profits divided by output. Okay, so if I profit more, do I want to invest more as well? Or should it be a negative function of the interest I pay? Okay, as we see very often in textbooks, economic textbooks. Right, and another thing, so here we have two parameters, alpha 0, alpha 1. Are these large or small? Are they different between the industries that you're, or firms that you're modeling? Perhaps you would like to do some econometrics to get real life values for these parameters, and because probably if you do something absurd, really large, really small, it will have an effect on the whole economy. Or you could just perhaps scan through the literature to see if someone did it, or see what the model allows you to do, because if you're doing a simulation model, for instance, for certain values of these, too high or too low, the model might explode and give explode in a sense that give very large numbers that don't make an economic sense. Okay. A second part of our tips, which is probably something we should discuss more, but live. But when we build models, we build them because we want to study different topics, and we do models as a representation of something to address a specific research question. Okay, so it's not the best practice to want to do the largest, most complex model always. Probably is bad practice, actually. What I would say is that the relative size and complexity of different parts of what you're building as a model, so the economy or social stuff beyond the economy, such as time use or other forms of measuring well-being or health, for instance, or how much detail you want to have in energy demand and supply. You might want to have like an energy market with auctions and so on, or no, or technology, different energy sources and so on. So the choice of how large or complex each of these parts should be, I believe should be tailored to fit the research question you have in mind. So some things you could ask yourself that I try to ask myself sometimes are, do I want to have a theoretical result, or should I fit real world data because I want to give, I don't know, calculate a number or the size of an effect, first of all, because then you understand how aggregate you can do things or not. So for instance, the model that we just presented, which is aggregate for the globe, probably it can be fit. So in the actual model, it is fit to real world data, but it's hard to believe they will explain a lot of social phenomena, as there is a lot of difference between countries or continents, for instance. Okay. Second, how important it is to have many different groups of agents, of income sources, of energy goods, and so on, depends on how much or what you want to understand. You want to understand the transition from non-renewable to renewable energy. So probably it's a good idea to have a lot of energy goods and changing technologies. Okay, you want to understand income inequality, so it's probably a good idea to have different types of agents that earn income from different sources, and so on. Yeah, so do I want to study something that is probably short or long term? That probably informs me how much attention I should pay to technological progress, structural change or behavioral change, or the effects of climate change, right? I want to do something very short term, probably I'll not be affected by sea level rise, okay, which will probably take some time to be really meaningful in most parts of the earth. Or I want to do something that is in 3 years, maybe I can assume fixed technology without losing much. So here, a simple example, don't be scared. This is the transaction matrix from this article, of which I'm one of the authors. So that's just to give you an idea. So the idea of this model was to understand the distributional income distribution impact of climate policies. Okay, so we have different climate policies, and we wanted to understand whether they have a positive or negative distributional impact on income, in addition to its environmental impact. So what you can see here is that most of the sectors, institutional sectors, in the transaction matrix are different types of individuals. So we have low skill, middle skill, high skill individuals that might be either employed, unemployed, out of labor force, or retired, pensioners, DP. And here in the different transactions, I know that most of them are income sources or expenditures by these individuals. So we have wages, unemployment benefits, different other public benefits. This is for France, by the way. I have income taxes, other taxes, wealth tax, consumption. You can see here they earn interest on bonds and so on and so forth, but only the high skilled individuals on equities and receive profits. So this is just an example. So we wanted to build a model to understand the impact on income distribution. So most of the complexity, right, all of this and part of this is focused on different agents, different income sources. And that to get to this, which is, here you have three scenarios on the baseline, their effect in terms of greenhouse gas reduction, and their impact on the Gini coefficient, which expresses income inequality. Finally, I will not get into this now, but I will provide a list of different software that you might find useful to do different kinds of model during the lecture, and we can discuss, because maybe it's good if I listen to what would you like to do, but these are some of the things you should consider when choosing software. I will get more into that, and some of these are some useful databases, very general ones. Then there are more specific ones, but especially like CLAMS, World CLAMS, EU CLAMS is good because it provides a breakdown of input-output industries, but by skill and gender. if you want to study effect on skill distribution, effects of technological change on skill distribution and wage inequality, or on gender wage gap, for instance. Something I use a lot. Here you have Axial Base, which gives material and environmentally extended input-output matrices and so on, but we'll get more into that. I have gone way beyond the time they told me, almost half an hour beyond, so I have to close now. This is my email if you want to write, otherwise we will speak soon in a week, I guess. Thank you very much for listening, and yeah, that's it. See you soon. Bye. Have a good evening, afternoon, or morning. Bye-bye.